Okay, so we just finished off naming our first non-oxy acid, which was prefix hydro. Then the anion is chlorine, but we're going to call it, the anion is chloride, sorry, but we call it chloric acid. So see if you can name HF. It's another non-oxy acid. And I'm going to move on with our first oxy acid. So if you start with an acid that has oxygen in it, we don't use the prefix hydro. We just focus in on the anion, which in this case is sulfate. And then this is referred to as sulfur. Now, the ion SO4 2 minus is sulfate. And if it has the 8 ending, we give it the ic acid on the end. So this is sulfuric acid. So maybe name those next two compounds, HF and HNO3, what you think they would be called. Okay, HF, there's no oxygen there, so it's going to start with hydro. So hydro, and then we got the fluoride ion, so fluoride, but then we add the ic ending, so acid. So generally with these kinds of acids, we have hydro, and then ic acid, sort of our naming scheme. Going back to the oxy acid, HNO3, well, this is the anion nitrate. And so we're going to add ic. So this is nitric acid. Notice not hydronitric. Oh, a double acid there. Not hydronitric acid, just nitric acid. And the last example I'm going to go through would be the ite endings. So let's take a look at something like H. Oh, sorry, that should have been a 2 there. How am I getting sloppy? So let's say H2SO3 now, or HNO2. Now, this ion here is SO3 2 minus, and that would be sulfite. And if it's sulfite ending in ite, then it's us acid. So this here is sulfurous acid. And what do you think the last one would be? This HNO2. Well, NO2 is nitrite, so this is going to be nitrous acid. So there's just a few naming schemes for you, and sort of helpful to know when you call it hydro and when you don't call it hydro. So basically non-oxy and oxy acids there. Now there's a big section in the book that talks about common acids and bases. I'm going to skip over that, but you might find that interesting in terms of some of the properties of these chemicals and where they're used. But I'm going to move right on to what really H plus is. So what is H plus? So what is this thing they call H plus? And why does it cause acids to have these unique properties? What's going on here? Well, let's just go back a bit to Chem, maybe like Science 9, and we're looking at, say, hydrogen. So I think many kids, when they first learn hydrogen, they understand there's like a proton here, so like a proton. And then protons have positive charges, so if we're talking about the hydrogen atom, then there would be this electron. I'm going to kind of represent this in kind of like a Bohr model kind of way. So this electron here. And it kind of, you can think of it maybe for now just kind of going around. And so the atom of hydrogen has this nucleus of one proton and this outer electron orbiting around it. And of course, this area between the electron cloud and the proton, this distance here, is actually quite large considering the size of a proton and electron. You could look up these sizes online if you really want to, but that's a pretty big gap between them. So that's the hydrogen atom. So that's an atom of hydrogen. And so if you think about H plus, well, that's a hydrogen with a +1 charge. So how would you how would you get that? What would you have to do to the atom to get that charge? So you'd have to remove that electron. And of course, if you remove that electron, all you're really dealing with is a proton. So you have a single proton sitting there. So when Arrhenius said that acids have H's and these H pluses floating around, what he's really saying is you have a proton, a single proton there. And of course, that proton is a positive charge, single positive charge, but its location is incredibly small in space. It has this tiny little core with this huge positive charge, and it's no longer impeded by this electron cloud that was around it. So if you put a proton into water, if you actually have a proton, let's just represent it by saying H plus, and you put it into water, you might remember the Lewis diagram for water. You have these kind of like Mickey Mouse ears. I'll point them down right now. But oxygen actually has 8 valence electrons. So you have these 2 electrons being shared between the oxygen, hydrogen, and you got these unpaired electrons here. And so they are the atom is the molecule, is neutral. But then you have this proton sort of hanging out here, and it's positively charged, and it's obviously a very small region of space. And so what it will do actually is it will grab these electrons, it pulls the electrons and wraps it around there. And what you wind up getting is a new compound, probably new for most chemistry students in Chem 12, but a pretty important compound to understand. That really is water with an extra proton. And so you still have those electrons there. This isn't the actual shape of it, but this here, because you've gained a proton to this actually has a positive charge now. It's because all you've really done is stuck a proton onto the oxygen. Now, the faster way to write this is H3O plus, and that compound is now called hydronium. So the hydronium ion. And that's really what happens when you have H plus in water. You don't actually have free floating protons in the water. That is just not going to happen. So in some ways, Arrhenius was wrong in that acids have these H pluses floating around in them and stuff like that. They don't actually just float independently around. They actually bind to the water and create a new compound called hydronium. And so in a lot of books, you'll see H plus written, and then you'll see H3O plus written. And it's important to understand they're really talking about the same thing. I'm assuming that this is just sort of a shorthand of the old way of writing it, but what's really in the water is this hydronium. And there's actually different types of hydronium out there, and if you want to look them up, you can see different structures of hydronium that exist, but in Chem 12, H3O plus is the primary one that we'll be focusing in on. And so really what we want you to move away from is this idea that H pluses are in the water. There actually is no H pluses in the water. It's hydronium. It's pretty much all hydronium at this point. So that's sort of our new topic we're getting into here. So if we look at, let me just here. So let's take a look at an example then. So let's say you had H3O. Or sorry, HNO. Let's do that. Sorry, HNO3. Let's do that. So nitric acid here. So under the Arrhenius definition, grade 11 chemistry, I think a lot of students would have said, well, this makes H plus and NO3 minus. And that's kind of how you were probably taught it. It has this H plus part. That's why it's an acid. But actually, if you put HNO3 into water, I'm going to leave phase states out for now because I'm just more focusing in on what's actually happening here. Is what you wind up getting is the H from the HNO3, so this H here, attaching to the water to make hydronium. So you actually get hydronium forming. And you still have the NO3 minus. So I guess in terms of what you already knew, you still get that ion in the water. So that's still the same concept. But instead of saying what Arrhenius would have said, or maybe your Chem 11 teachers would have said, is that you actually don't have H plus in the water now. You actually have hydronium in the water. That is the new way of thinking about acids. So they produce hydronium, not H plus. But once again, a lot of books kind of interchange these topics, but really factually there's hydronium in the water, not free floating protons. Okay, so that's definitely something new here. Okay, so who are these Bronsted-Lowry characters? What was their big contribution here? Because we said at the beginning, way up here, We said Arrhenius said H pluses for acids, OH for bases, and you mix an acid and a base together, you get salt and water.